Hello, civil engineers. Welcome back to the lecture. So what happened is in the previous lecture we were going through, the construction joint and all. One thing I forgot to tell there. Now, like what I told is, whenever you're stopping the concrete in the beam, you should pick the point of contraflexion. So what is point of contraflexion? I mean, where exactly is the point of contraflexion? We don't. Of course, we know that, but if I ask you, you people don't know. So that is why in the you can see this particular drawing is mentioning you have to stop it at L by 4 distance. You see here, this is a column, okay? This entire thing is column actually. This entire thing is column. Yeah, this entire thing is column, okay? From the face of the column, this is your face. From the face of your column, this joint, whatever you're having, no, this construction joint, what you're living like this. So it should be 0.25 into L. 0.25 means 1 by 4. 1 by 4 means L by 4. L by 4 means that is a place where your point of contraflexion will happen. Okay, so from the face of the column, for example, if I have a beam of 10 meter, let us say 10 meter, where is the point of contraflexion? 10 by 4, 2.5. So from the face of the column up to 2.5 meter, I'll do the casting, and there I'll give this construction joint. Understood? So yes, mentioned 0.25 into L. Simple. Yeah. Now after that, same we have a construction joint in the slab also. Slab, I'll take it later. Now we'll understand something good. That is about the beam reinforcement part. We understood about the column, right? Now try to understand typical beam reinforcement. Again, most of the things you know, right? How shall I start? How shall I start this? Okay. Hmm. So a lot of things to explain, no? How shall I start? Yeah, anyway, let me start from here. Hmm. So what shall I do is, see, this is clear span. Always remember, clear span is from the this part. This is column from inner to inner. From this column inner to this column inner, we call that as a clear span. And what is effective span? Effective span is always from the center of the column to the center of the column. If I measure, it becomes my effective span. Understood? Yeah. Now again, the same concept holds good here. Near the support, this is your support, right? You'll be providing your, what is that, stirrup at a very close distance to each other. You can see, you can I mean, yeah, you can check here also. See, they're very close to each other, right? Because why it is so? Because they are near the support, and that is where the shear force is maximum. And also that is because from earthquake detailing we are supposed to do. In the center, you can see this is the center portion. It increase the spacing. The spacing is increased in the center portion. Understood? This much is understood. Good. Now, I told you that when it came to the lapping part, I told you in the beam, you should do the lapping. For the top reinforcement, you should do at the lapping at the center. And if it is a bottom near the support, yeah, within L by 4, you can do. Now, same thing you can see. I'll remove everything now. I'll just teach you this one. See here. He's showing something here. This guy is showing something here. What is that? Exactly. This is lapping. You can see the bar has been lapped. See? You can see the bar has been lapped. And he's telling us you have to lap it here. And where did he lap? Exactly at the center. This is the entire span, isn't it? Exactly at the center he has lapped. Which bar? Top bar. Now we look at the bottom bar. Bottom bar, is there any lapping? Right now it's not lapping here, but here it has lapped. If I come here, I told you bottom bar should be lapped within L by 4, but here there is no lapping. You can see this bar. See here, they have lapped it inside. Isn't it? Why? Always remember you can do the lapping within L by 4. Usually if you lap it exactly at your column and the beam junction, that is wherever you have column and beam intersecting, in between that if you lap, that is good. So that is why they are telling you can lap it here for the bottom reinforcement. Bottom he has not shown in the middle. Why? Because in bottom at this particular point, your bending moment will be maximum. Which bending moment? Sagging bending moment. So we'll not lap. We'll lap it at the junction. Within L by 4 you can do. See, actually, if it is not earthquake resistant structure, then you can lap within L by 4. You up to here you have chance. From here you have chance. You can lap anywhere. But here, usually they have lapped it from earthquake point of view. You can even lap up to this distance. Beyond this, you should not go. Okay. So as far as possible, try to do within this much junction only. You can do the lapping, which they have shown it here. What should be your lap length? Actually, lap length will be given. If it is not given lap length, you can, whatever is your development length, that much you can provide your lap length. So this is your lap length actually. But if it is not given, you can, what you can what you can do, whatever is your development length, you can make use of it. If your development length 15 today, 15 to, let us say, if you're using a 12 diameter bar, 500 lapping can be done. Understood? Yeah. Now one more thing. See, wherever you have done the lapping, no, you have done the lapping in this portion. What these people have done, they have closely spaced the stirrup. You can see here, the stirrup is closely spaced. Actually, in the center portion, stirrup spacing was increasing. But since you have done the lapping here, again, what will happen lapping? It's a weak joint. When you do the lapping, it's a weak joint. In order to make your concrete and the stirrup confined, what practices we adopt is wherever we do the lapping, no, we place our stirrup very close to each other. Again, this provision is adopted only in the ductile detailing. That means if I refer IS 13920, this is IS 13920 code book from earthquake resistant. Okay. In that cases, you're supposed to follow this. But if it is a normal construction practice you're adopting, I mean, if you're not putting your structure in the earthquake resistance zone, then you don't have to do this. So it's done something here. Okay. Wherever you do the lapping, the center portion, no, they have, I mean, what they have done, they have brought the stirrup very close to each other. Why it is done? So that a good confinement will happen, because it is a point where, again, the failure may happen. Okay. So that is why in order to confine that, we have provided very close to each other stirrup. But it's only from ductile detailing point of view. Understood the concept? Next comes the development length. So you know what is development length. Where your development length start? If this is my column, if this is my column, from the face of the column, my development length will start. Right? This is the face of the column. From here, it will start. It will go all the way like this. This is my development length, which is mentioned here. LD plus 10 times the diameter is shown like this. Understood? This is called as development length. If it is a normal structure, then it is only LD. If it is an earthquake resistant structure, and if you're following a ductile detailing, it will be LD plus 10 times the diameter of the bar. Got it? For the top and even for the bottom bar also, it's the same thing. Bottom also, you have to follow the same thing like this. Okay? They mentioned it here. Understood? It's written here. Development length in tension, dB is a bar diameter. Got it? Good. After that, what is left out? After that, you can see the top extra bar. This is your top left extra. You can see this bar. This is your top left extra bar, isn't it? So from the face of the column, how much it has to be extended, that is mentioned here. It has to be extended up to 0.3 into L. What is L1? L1 is your effective span. L1 is your effective span. See, few people take effective span, few people take clear span, few people take 0.25, few people take 0.3. End of the day, nothing much difference will come. Okay. You're getting my point? So if this is 10 meters, so 10 divided, I mean 0.3 into 10 will be 3.33, right? So this distance will be top left extra will extend up to 3.33 meter. Again, from where all these things are taken, again, all these things are written in SP34 and you follow all those things. Okay. He has not written it here. Actually, it's written in this only. Maybe I need to search, or maybe there's another. I cannot find it here. But everything, anyhow, it's taken from this code book only. Okay. They'll be mentioning it here. Based on that, you can take it. Understood? After that, what is left out? Yeah. They show something here, no? What is written? 50 maximum. So what do you mean by 50 maximum? It means the first stirrup that you place in your beam should be at a maximum of 50 gap. That means tell us practically, sir. And this is how it looks practically. Okay. I had one image. Okay, it's here. See, this is a stirrup what you're placing, isn't it? This is a stirrup what you're placing. This one, right? So this is a column. From the face of the column, this gap, that means your first stirrup should not be more than at 50 gap. That means this, if this is the face of my column, let us say this is my face of the column, isn't it? And this is my first stirrup. The gap between my column and the first stirrup should not be more than 50 So again, why it is so? Because we know that at this particular point, your shear force is maximum. So what we try to do is we need to confine that. So if you give too much gap, then again, what will happen is due to more shear and all, cracks may try to propagate like this. In order to stop that, what we provide is we provide a two-leg stirrup. So this is leg number one, this is leg number two. So both the leg will be effective in resisting the shear cracks which will occur over there. Keeping that in mind, and also 50 in the sense, Usually when you do the binding, that means you cannot simply keep your stirrup here. No, you require one bar bender who can at least put his hand and do the binding of it. So this 50 gap is minimum required. You cannot give a gap of 20 because because when you put your stirrup here, the barbender has to put his hand and he has to do the tying of it. At least 50 gap should be there for him to freely rotate his binding wire, and also that chisel what he has with his hand. I don't exactly know the name of that. So that is the reason 50 is kept. Again, from because here your shear force is maximum, keeping that in point, yeah, that in mind, they have given 50 Okay, you can give in 55 but the code says that 50 is maximum. So try to limit within that. Simple. I think most of the things I've covered here. dB and all means it's a diameter of the bar. It is telling us. And this is, yeah, last one thing is left out. Last one thing is this one, your bottom curtailment bar. So bottom curtailment bar, till what distance it has to stop. So from the face of the column, you give 0.15 into L1. From the face of the column, leave 0.15 into L1. Suppose if it is a 10-meter span, so 0.5 in, 0.15 into 10 is 1.5. From here, you leave a gap of 1.5 meter. From here, you leave a gap of 1.5 meter. And then this bottom curtailment bar will go up to here. Understood the concept? Chalo. Hmm. This is done. 0.3 into L1 is done. This is development length. I taught you. Next, again, same thing. Only the difference is what you know. Only, there is no much difference also. Yeah, there is no difference also. Yeah, that's it. That is all. That was all about the beam one. Again, since it's a continuous support, now you know this is continuous because if this is a column, here also I have a beam. Here also I have a beam. So you'll be providing a top extra. Okay, it won't come all the time. Depends on the area of steel requirement. So then, to what extension you have to take it? Again, same thing. From the face of the column, your top left extra will go 0.3 into L1. Again, on the right side also, it will go up to 0.3 into L1. Now here, there is something they have written. 0.3 L1 or L2, 0.3 L1 or L2. And here he is mentioning L1 or L2, whichever is greater. That means we have two span now, right? We have two spans. One is this span, this span. From here to here, we have one span. And then here to here, let us say there is another span. It's a two span beam. So let us say this is 6 meter and this is 7 meter. Out of 6 and 7, which is higher? 7 meter. So whichever is higher, you will take. That means for 0.3 into 7, I'll do. Because actually, if I'm looking for this side, I need to consider 6 meter. If I'm looking on right side, then I have to take 7 meter. So what the code says, don't do like that. Out of L1 and L2, this is L1 and this is L2. Whichever is higher, you take that. So 7 is higher, no? So 0.3 into 7 you do. And whatever length you get, you provide up to here, top right. And top left also, you take 0.3 into 7. That is what the code says. Okay. Hmm. Why it says like that? Again, keeping an execution point of view. Otherwise, again, on the site, what will happen? For 6 into 0.3 you do. Again, 0.3 into 7 you do. Here you will get some different length. Here you will get some different length. Why you want to unnecessary create problem? So always you if you take a higher one, you're always on the safer side only. So that is why we have gone with L1 by L2, whichever is greater. Okay. And then whenever you're lapping the bottom steel, make sure you're lapping your bottom steel within L by 4. But if you're lapping at a column and a beam junction, always good. And you have to lap it like this. Okay. You have to lap it like this. Hmm? Yeah. I think, yeah, everything I've explained you here. So most of the things is done. Uh, yeah. Then this one thing is left out. Anchorage of beam bars in interior joints. So anchorage of bar of beam in interior joints means what actually happens, you know. See, usually what happens is practically on the side, if this is my column, this is my column. How shall I do this? Hmm. I'll do it here. Usually what happens on the side, if this is your column, and always your beam reinforcement, if this is my column reinforcement, if this is my column, your beam reinforcement should actually pass inside the column reinforcement. But due to the space restriction, what happens is if I have 3 bar, only 2 bar I'll pass it through the column. Another 1 bar I'll pass it outside the column. So that is again a wrong construction practice. So he says us in this, he's telling us whenever you have such what you call difficulties on the side, you bring your beam bar and you put a crank and take it inside the column and take a crank and take it outside. You're getting my point. Actually, what happens? What these bar benders they do? If you have 3 bar, this 2 bar will go. This 2 bar will easily pass through the column. The 3rd bar usually it will not pass. Okay. What they do is they take it from outside only. From outside only they will pass and then they will bring it like this, which is not a right construction practice. So in that case, you bring a bar, you give a small crank, and then you inside. You bend and take inside, then again give a small crank and take it outside. So this is a right construction practice. So that is what is mentioned. Beam reinforcement. This is your column, what you have. This is beam reinforcement. This is how you're supposed to do. I'll show you one practical image of this also. I have a practical image for this. Give me a minute. Yeah, can you see it? See, this is a column what we had. Okay. So column dimension is this width is less. So now what happened? Actually, if in the local construction practice, what they would have done, no, 1 bar he would have easily taken from inside. This bar he would have taken from outside and brought it. So that is not a right construction practice. So what you do, 1 bar anyhow it will go, right? The 2nd bar, what you do, see, he has brought a bar, gave a crank like this. Now he has taken inside. Once you have taken inside, from here you again he has given a crank, and from there he has taken outside. Got it? So this is how you are supposed to do the construction on the site. So you can see it. I don't know how the video plays, but at least something you can see. You can see again here also same thing. Now here what he has done, same again. This bar anyhow it was passing. This won't pass. Yeah, if this crank was not given, no, this bar bender would have passed it from outside easily. Because why they do? It is easy for them to do the execution. No. Now what happened? Now the bar bender has to give a crank something like this and then take it inside. So it is the extra work for him, right? So that is why they try to avoid all these things. So being a site engineer, you should keep all these things in mind. So that is why these engineers know people will do something like that. So he's mentioning everything here. We don't allow you to do like that. You need to pass it inside the what is that column. Okay. The same thing is mentioned in SP34 also. If you refer SP34, the same thing they have told it in the SP34 also. Yeah. Got it right? I think most of the things I've explained you. And now we'll go finally to the slab portion. Okay, I'll finish the slab also. The slab is again simple. Slab like we do for the beam, no? The same is a slab. What will happen? No? See, again for the slab, you'll be providing top left extra, which will only go 0.15 into L1. You know that. And in the middle portion, this is a slab. You have a slab on this side. You have a slab on this side. So it becomes a continuous span. So again, when you provide a top extra on the left side, you go 0.3 into L1. And here also it will be a top right extra 0.3 into L2. And again, same thing. L1 by L2, whichever is greater, like we did for the beam, no? Same for the slab. There's nothing much change in the slab. Apart from that, even the bottom also bar here. This is your bottom bar, what you provide in the slab, no? Usually we don't do it like this. We actually provide full only, but still okay. They have given it like that. If you're providing a bar like this, if you are curtailing, then from here you leave a gap of 0.15 into L1. From here you leave 0.15 into L1. Okay, fine. Got it? This much is understood. Then again, another thing, yeah, very important, which is something, interesting. You should understand. See here, this is not a complete development length. If you remember, in the beam, we were giving LD plus 10 times the LD, sorry, plus 10 times the diameter of the bar. But in the slab, usually your slab reinforcement will come like this, and only a small portion will get embedded into your beam. That is 8 times the diameter of the bar is mentioning. Same here also. Got it? So it's not like development length plus 10 times the diameter of the bar. Why it is so? In the beam, you are doing the same thing, and your beam and slab is similar. Why you're not doing that? Because I told you that actually your slab is a kind of a simply supported, but due to the fixity of your slab reinforcement with your beam reinforcement, due to a small fixity, what will happen? Negative bending moment arises. So that is why what happens is we get this negative bending moment like this. That is why this top left extra is given. Okay, that's the first thing. Second, yeah, if you do this completely like this, no, if you do complete development length like 10D, development length plus 10D, it's like instead of giving this much, see, this is your junction, instead of giving only small development length, this much, if you give completely, no, what will happen? Complete fixity will happen. Due to this complete fixity, whatever moments will come from the slab, no, all the moments, whatever will come, everything will be passed on to the this thing, beam here. So as a result of that, huge bending moment will come. We don't want that to happen. So that is why what we are going to do, small only we are giving, only this much, only LD, 8 times the diameter. Don't give it completely like this. Okay. So usually practically on the site also we do the same thing. This will be 8 times the diameter. If you're using a 10 diameter bar, 8 into 10 is 80 mm. So this will be hardly 80 mm bend you are going to give. Okay. 80 or even 100 mm you can give. It's mentioned 8 into dia. So if you're using a 10 diameter bar, 8 into 10 is 80 mm. Simple. Understood the concept? Yeah. The same thing here also everywhere. And then lapping again, same thing. Whatever you did in the beam, no, same lapping. You can lap the bottom bar near this junction. That is your, what is that? Column beam junction. And top bar, anyhow, there won't be a lapping in the top bar in case of slab and all. Okay, fine. Top left extra will extend only 0.15 into L1. That's it. Okay, yeah. Again, another question. I don't know whether I explained you or not. Why this is 0.15 into L? Why it is not 0.3? Because here, anyhow, you are giving 0.3, but why it is only stopped at 0.15? The reason is very simple, because for this particular slab, we have only one beam on this direction, right? So because of this small fixity, huge bending moment will not occur, or your, what is that, intensity of your bending moment is not too much. It's a small bending moment we get. So the intensity of the bending moment has been found that it is somewhere up to 0.15 only, since you have only this side. But whereas it will go like this, but whereas this, it's a continuous support. Whereas this is a continuous support, due to the slab on this side and slab on this side, a huge negative bending moment is created. And since there's a huge negative bending moment is created, the impact of that bending moment is almost at 0.3 and 0.3 on left and right side. So since the impact is on higher side, this impact I'm telling, when I say impact, this one, up to this distance, you are getting that negative bending moment effect is up to this distance. So that is why we are giving 0.3 and 0.3. Whereas here, this impact, this negative bending moment impact is on a lower side, and it's what you call up to this length only that effect will be seen. And after that, this negative will turn into a positive, and then it will come into sagging. Only up to this. So this portion is 0.15. So why it is 0.15 only? Why it is not 0.20? Again, people have seen through experience and all, they have done they might have done the measurement, and a lot of studies might have been done. And finally they found, okay, we'll go with 0.15. You can take 0.16 also, nothing will happen. But you shouldn't come below this. Even if you go beyond this, no problem. Got it? Yeah. Now coming to the last portion, typical construction joint. Column we understood, beam we understood. Now typical construction joint in slab. Whatever concept we applied in beam, same thing in the slab. Okay. So again, see, if you're stopping your slab concreting, then if you just started the slab, if this is a discontinuous edge, okay, that means you don't have slab here. This is the first slab you are starting. Then if you're stopping, it has to be only up to 0.15 into L. Got it? So if your slab, let us say if it is 4 meter, what is 0.15 into 4? 0.15 into 4. 0.6. 0.15 into 4. 0.6. Okay. So within 0.6, within 600 mm, you have to stop it. And when you stop, make sure you're not stopping it vertically. You just have to give a something like this. You stop here, then you extend like this and give it here. So that tomorrow when you place the concrete, it will get a good bond here. Understood? This is for the discontinuous support. But usually what happens is uh, we have to understand about the continuous support. For the continuous support, what they are telling, continuous support means it was 0.25 into L in the case of beam. Same here, but instead of 0.25, they have made 0.3. So here you have to stop up to 0.3. Okay, and then you have to stop it like this always for the slab. For the beam, it was like something like this, no? Why it is like this here? For the slab, see, for the beam, it was something like this, isn't it? Why for the slab it is only like this? Because slab depth is how much? Slab thickness is hardly 150. Beam was like 450, 600. So since it was a 600 mm beam, you could have easily stopped like this. Like this you bring, you had enough gap and all, you could have stopped like this. In case of slab, your slab thickness is only this much, 150. So what you'll do? So you make it in only two steps. You bring one step and second step. Understood? So that is why it is only, uh, uh, since slab thickness is small, we are doing like this. And that's it. That is enough. Now he is telling us, again, if you want to be more precise, tell me how much is this? How much is this? He's telling d by 2. Whatever is your thickness of the slab, you divide by 2. My slab thickness, if it is 150, 150 divided by 2 is 75. From here, you bring 75, stop it, bring like this, stop it, finish. 75, 75 is 150. Simple. Understood? Remember all these things. Okay, because tomorrow on the site, let us say you don't get a drawing like this, and something happened on the site. It started to rain so heavily that you wanted to stop the slab concreting. So wherever you cannot stop the slab concreting wherever you like, right? So in that case, if you have just started the slab and you are at the discontinuous support, you can go up to 0.15 into L and you can stop. But if you are concreted for almost 2 hours and you are crossed somewhere, you are somewhere close near the continuous support, then 0.3 into L, you are supposed to stop it. And you should know the concept. Again, same concept here. This is a point where a point of contraflexure will happen. So we'll stop it here. And this is the point of contraflexure. Okay, simple. All these things you should understand. Only then you are fit to be called as a technical civil engineer. Okay, yeah, that's enough. Everything I've explained you. Only the thing, it's up to you how much you're going to retain and how much you will practice and how much you'll remember. That's it. Okay. What else is this? P/2. So this is nothing. This is what I mean. It's written P and P/2. No. So actually, what happens? The distance between the two rebar is telling us P. And when you place your first rebar, you should leave a gap, right? How much gap it has to be left, that is trying to tell. If a spacing between the two bar is 150 mm, what is 150 by 2? 75. So you can give a gap up to 75, and then you can place your first rebar in the slab. You understood the concept? Is mentioning the distance between the two rebar is P. And from this gap to here, you should leave how much gap? I don't know. So P is mentioning, so P/2, 150 if I take the distance between the two bar in the slab. If it is 125, 125 divided by 2 is how much? How much it is? 62.5? Yeah, 62.5. In that case, you leave a gap of 62 and you can place your first rebar here. Okay. Not, you can, if you want, you can follow, but usually most of us don't follow. What we do is, wherever we have stopped, no, from there we leave a cover of 25 mm and then we start with the placing of the first bar. But you can follow this also. Nothing much technical in that. Yeah, that's it. I feel I've covered everything. This is not required. This is from a steel point of view. When I take up the PEB drawings, I'll explain you there. This is something for the secondary beam, not required. We don't provide secondary beam nowadays in this way, not required. This lapping part, this cranking part and all, I've explained you. The intel is explained. Yeah, that's it. So I think last one part is left out. I'll take it. That is about the another drawing what I had. That I'll take up in the next lecture. So I'll see you in the next lecture. Thank you.